Hi, everybody. So I wanted to go over this particular problem. This problem is really hard, and it's hard, I think, for two reasons. One, it's hard because it would seem that you could handle it quite simply. Um, and I'll talk about the simple wrong solution in a second. And then it's hard because of how we have to index all of our velocities and things like that. But what is essentially happening in this problem is you have a guy or a girl, an explorer, who's trying to get across this river. And this river is 120 meters wide in the y hat direction, positive y. And he wants to get to a point that we're going to say in this problem that x is positive to the right and y is positive upward. And he wants to get, and the river is flowing this way at a rate of 1.3 meters per second in the positive x hat direction. He wants to get to a point that's 74 miles upstream. So if this is our 0 point for x, this is negative 74 m, okay, in the x hat direction. And his boat, relative to the river, his boat can do 6.8 meters per second. So you might think that you could just point the boat there. Sorry, that's a really bad drawing. Might think that you can just point the boat at this point, figure out what this angle is, and figure out what this radial vector is, and you've got it solved, right? Knowing that if you know the distance, right, because x is v times t, you know v of the boat. If you figure out how long r is, so r over b of the boat should give you the time, right? That won't work. And why won't it work? You got to think about this, because you would think this would totally work. It won't work because the river is actually moving, and the boat's moving relative to the river. So he has the motion relative to the river, but he also has the motion of the river relative to the ground. So his velocity of the boat relative to the ground is his velocity of the boat relative to the river plus the velocity of the river relative to the ground. Remember that VA over B plus VB over C gives you VA over C. The B's cancel out, right? That's how we do relative velocity. Let me do a simpler problem first. In this problem, instead of trying to get upstream, I just want to get across. So I want to go the 120 meters in the y across. And the river is flowing at, what was it, 1.2, 1.3. So the river has a velocity relative to the ground of 1.3 meters per second in the x hat direction. And his boat, he's trying to just get to x is equal to 0. His boat, at any angle, can do 6.8. So what we're going to have to do is he's going to have to move so that, in effect, he doesn't go in the x direction at all. He doesn't want v of x to equal anything. The velocity of a boat to the ground in x has to equal 0. So he's going to point it at some angle, right? The velocity of a boat relative to the river at some angle such that this is true. And we know that this is the boat relative to the river in the x hat direction plus the river relative to the ground in the x hat direction. And we already know that. This is right here. This is 1.3 meters per second, okay? Now, what is b relative to the river? So in the x hat direction, we have v in the x and v in the y if VBR is being pointed at some angle. So this is actually negative, because our x direction is that way, negative v b over r times sine theta in the x hat direction. So we know that 0 has to equal v b over r, which is just our magnitude, our 6.8, with a minus sign, times sine of the angle, times x hat, plus v r over g in the x hat. And this, if I cancel my r's, will give me v b over g in the x hat, which is 0. Now knowing that, I can then set these things equal to 0 and move this one over, and I get v b over r sine theta plus, or sorry, not plus, is equal to v r over g, and solving for sine of theta, I get v river over g over v b over r, which is 1.3 over 6.8. And if I take the arc sine of that, right, if I take theta is arc sine of 1.3 over 6.8, I get that this should be arc sine of 1.3 divided by 6.8 is 11.2 degrees. So this is 11.02 degrees. So he has to point it at an angle of 11.02 just to get, just to stay aligned with the y-axis, if you will. Okay, so his total motion is vb over g in the x hat is 0, but he's actually doing, he's actually got this thing pointed vb over r sine theta, right? His actual motion is this in the x hat. So his v, and we'll call it vb over r. So this is vb over r in the x, and this is vb over r in the y hat. Okay, so we know that vb over r times sine of theta is r vb over r in the x hat direction. And that will give us, was it 6.8 and 11? So 6.8 meters per second and 11.02 degrees. So 6.8 times sine of 11.02 is 1.3, essentially, meters per second in the negative direction. Why is it negative? Because when we look at our picture, right, we're taking the angle, this is x is equal to 0. So we're really off the x-axis. We're really at 11.02 plus 90 degrees. So we're really at 101.02 degrees from the x-axis, right? That's our bearing if we want to take it from the x-axis. We do that in this problem at the end. But that's going to give us a negative 1.3 meters per second in the x hat direction. In the y, VB over R of y, right, we're going to have VB over R cos theta, which is 6.8 cosine of 11.02, which is 6.675 meters per second. Now, if we want to know the time that it takes them to get across, we just have to multiply this by time, right? So we can take the, again, the y is v in the y times t, or t is y over v of y. And we said y was 120 and this was 6.675. So 120 divided by 6.675 is about 18 seconds, okay? And if we multiply this by 18 seconds and we add the river to it, so if our Vx total, right, is VBR sine theta with a minus sign plus 1.3, right? This ends up being 0. That's easy enough to see, right? This is, so our motion is we're basically having to fight the current, right? Fighting the current, and we can see that just to get across to the other side, we've got to add 11.02 degrees. So what I'm getting at here, what I'm trying to get at here, is that if we didn't, right? If we didn't add that, what would happen as we went across is we would end up going somewhere over here, right? If we just pointed right across the river. And so we've decided that we're going to go at 11, let's just call it 11 degrees, right? If we go at 11 degrees, our actual path is straight across. So our velocity of the boat versus the ground is 0 in the x-hat plus 6.675 meters per second in the y-hat, okay? So we have to aim at it just at 11 to do that. So in order to get across the river, basically, and hit this point that's here, right? Trying to figure out what it was. So if we want to hit a point that's 74 meters upstream, so x is minus 74, we're going to have to also add some angle so that we're actually aiming for a point even further upstream so that we account for how much the river's pushing us downstream, right? So we can't just take the angle straight to there. That's the actual angle that we would see, but that's not the angle we're pointed at, because we're going to have to add some angle to account for the river's motion as well. Okay, so how we do this is, imagine now, right, that the river, we want to go straight across and the river's not even here, right? To get here, to get to a point here, then yes, this is x, this is y, and we simply aim at that point and figure out the time. But we've also got to account for the extra motion that we're going to have here. So we're really going to aim for somewhere further up the river. And this x here will be 1.3 times t. That'll be the extra distance that the river is going to carry us downstream that we have to account for. So mathematically, what we're looking for is we're looking for x is equal to negative 74 meters, y is equal to 120 meters in the y-hat. This is in the x-hat. Remember, it's negative. And we're looking for some velocity, right, that will carry us there times t. And that's where our indexes are going to get a little messy, okay? Because we might want to call this, we want to call this v of the boat versus the ground. And so we want to say that the boat versus the river in the x-hat plus the river versus the ground in the y, or in the x-hat, and in the y-hat, we want the boat versus the river in the y-hat plus the velocity of the river versus the ground in the y-hat. Now we know our river is flowing, river versus ground is flowing at 1.3 meters per second in the x-hat direction only. This is x, this is y. So this is going to be 0, but we're still going to get this. So our y is actually a little bit easier to do. VB versus the ground, y-hat, is VBR y. Remember, we're going cosine because we're going for this angle, cos theta. If we multiply this by t, right, what we get is we get our y distance. So 120 is equal to what I'm going to call our VBG in the y-hat. Now, we need to figure out what our VBG in the x-hat is. We're going to have to go negative. So this has to be negative sine theta. Again, we're going to multiply these by time. Minus, that's the part that covers our motion minus the river versus the ground times t. Now this, I'm just going to leave, I'm going to call this for now, I'm going to call this VBR. Okay, just for now, VBR times t minus VR over g times t. And this, right, at the end of the day, we know what this will end up being. This will have to end up being our x distance, our minus 74 meters. That's what VBG over x in the x hat time times t is going to have to equal negative 74 meters. Okay, so what I want to do now is I want to solve this for VBRT. And how I'm going to do that is just remember that this thing's negative, right? Remember that that's got to be a negative. So I get VB over river times T. If I move this over and I have a negative, I'm sorry, this is plus. If I move this over, I get negative 74 minus V river over ground times T. I can cancel all the minus signs. So what I get is I get 74 plus 1.3, that was the velocity of the river to the ground, times T. Okay? Now, I know the velocity of the river, this was in our x direction, times T in the y hat was 120 meters. Okay? What I want is I want to know what this is. This is actually what I'm searching for. Okay? The reason why is I know this. This becomes VB over R squared times T squared. And it's equal to VB over R in the X hat times T plus VB over R in the Y hat times T. And remember again, we know what these are. This is 74 meters plus 1.3 T squared plus 120 squared. Okay? And this was 6.8, I believe. 6.8. So this is 6.8 squared. I'm going to move to a new slide. And I noticed that I have 6.8 squared times T squared is equal to, if I do this, I get 74 squared plus 2 times 1.3 times 74 times T. So when we do this thing, remember that's 1.3 times T. I get 74 times 1.3 times T. I get two of them. And then I get 1.3 T squared, which is 1.3 squared times T squared. And then finally, I have to add that final term, which is 120 squared. I'm going to make this into a quadratic so I can solve it for time. Setting this equal to 0 and adding together the T squared terms, I see that I have 1.3 squared minus 6.8 squared times T squared plus I have 2 times 1.3 times 7.4 times T plus I have 74 squared plus 120 squared, right? Okay, so this is my A, this is my B, and this is my C. And let's write down what these are really fast. 1.3 times 1.3 plus 6.8, sorry, 1.3 times 1.3 minus 6.8 times 6.8 gives me negative 44.55 for A. 2 times 1.3 times 7.4 gives me 192.4, that's positive. And finally, 74 times 74 plus 120 times 120 gives me 19,876. Now remember, T is going to give me two values, but I put in minus B, B squared minus 4AC over 2 times A. And when I do this, I get negative 192.4 plus or minus 192.4 squared minus 4 times minus 4455 times 19876. All right, that's my A, that's my C. These negative signs become positive, and I put it all over 2 times 44.55 with a negative sign. So I'm going to do that square root real fast. 192.4 times 192.4 plus 4 times 44.55 times 19876. 4 times 4.55 times 19876. And then I take the square root of that, and I get 1891. So I get minus 192.4 plus or minus 1891.8 over, and this is 88, so 44.55 times 2, 89.1 over negative 89.1. Okay. Now, I need time to be positive. So whatever I get in the top had better be negative. Okay. If I do negative 192 plus 1891, I'm going to get a positive in the top and a negative in the bottom. So I can't do that. I need to add the negatives. So 1891.8 plus 192.4, divide that by 89.1, the negative signs cancel, and I get 23.4 seconds. I was double checking myself before I went any further. So 23.4 seconds. That is my time. Okay. So that's how long it takes to get across the river. Now, what angle am I going to be at? So I need to know, if I go all the way back here, I need to know what angle VB versus the ground is at. And so what I really need to know is I need to know what VB versus the river, what angle this thing is at. So my angle is arctan, and remember that this will be my VB over R in the X, and this will be my VB R in the Y. So I'm actually doing the tangent of the opposite over the adjacent, which is VB R in the X over VB R over R in the Y. Now, what are these? So remember that VB over R in the X hat was equal to times T. Sorry, I need to multiply these by T. So what were these? And if we go back and look, these are the same things that were in here and in here, right? So we want to find those. So VBR over X times T is equal to 74 plus 1.3 times 3. And that is 74 plus 1.3 times 24.3, or 23.4, which is 104.42. And VBRY times T was 120. So our angle with respect to the y-axis is 104.42 over 120. And that equals arctan of 104.42 divided by 120 gives us 41 degrees, 41.03 degrees actually. However, that angle is to the y-axis, and they want, in Wiley, they want us to take it to the x, so we need to add 90. And that gives us 131.03 degrees from the positive x-axis. If we go back and look at our solution, our angle was 131 and our time was 23.4, which is exactly what we got. I did it in reverse order from how they did it, but what we were doing was we were basically trying to find, we knew this was negative 74, and then we had to add the x distance due to the river. And that distance due to the river was 1.3 times t. And this distance we had to get from our V boat versus the river sine of our original angle. So what we ended up having, we couldn't just figure out what this angle was. We had to figure out how much further up the bank it actually went. And so what this looks like is this boat is trying to cross the river, and what you see is it makes a path straight to P, right? Straight to the point that's negative 74 meters. But it's actually angled at a much greater angle. And that greater angle was whatever, 131. So it looks like you should only need to be about 11 degrees to get over there. But you really need to be at 40 degrees because the river is pushing you back the whole time. And if you went here, you would never make it there. If you aim just for that, you would end up like here somewhere. So you need to aim a little bit further to the left, further down the bank, in order to account for the river moving you relative to the ground while you're in it. These problems are super hard. They're annoyingly hard. And as I stated, the whole deal with indexing, it's really great. I mean, it's a really good way to explain it, especially in the going straight across, that as we're traveling this way, due to the boat versus the river, and the river is sending us this way, river versus the ground. Well, a good way to see that is that in the river's frame of reference, we're going straight. And in the ground's frame of reference, the river itself is moving downstream in the positive X. And so we need to account for this. We need to move in some way that we're going to cancel this with the X part of our motion while still continuing across. So yeah, it's a bit of a pain. Hopefully this makes some sense to you. In the solution, I'm going to post a picture of the solution that they give me in the book that kind of explains this. Hopefully it'll explain it a little bit better than I did to you if mine didn't make much sense. But I really just wanted to try to explain to you what is going on and kind of how you can do the math. However, the math gets a little wonky here because this right here is the boat relative to the ground is our BR, right? Plus our river and ground. But then here we switch over and we just want to find the angle and the velocities in the frame relative to the river. And so that's a little weird. It's a little messy. Hopefully, maybe at some point you'll find a clear way that explains this to you and a way to derive this. But yeah, essentially what you have to do is you have to figure out what the motion in the X is, and then solve for the motion of the boat versus the river. And that's a huge pain. Anyway, hopefully this helped. Talk to you guys later.